Okay, so good afternoon, everybody. So today I will be talking about the use of modular form theory to build SL2Z equivalent machine learning and discuss some of the application that we have, in particular in the financial industry. So the outline of the talk. So first I will start with some background and motivation, then discuss how do we build this equivalent machine learning algorithm, and then present you an application for the classification of a specific type of covariance matrices. And then I will conclude and shed some light on some further work that we have in mind. So let's start first by reminding ourselves about some link which exists between the space of specific type of covariance matrices and hyperbolic geometry. But before that, let's start with some very quick motivation regarding why we are interested in analyzing covariance matrices in finance. So we had a talk from Cody who already gave some hints about that. So the interesting thing is that when you think about covariance matrices, so it's going to give you information about how financial assets are evolving together. So in practice, you can see these covariance matrices are stochastic matrices lying in the SPD manifold, and understanding their dynamics has multiple applications, such as the portfolio optimization one that we saw in the previous presentation. So we do have several tools that are useful to analyze this type of matrices, and one of them is what we called random matrix theory. So this one is very helpful when, in particular, dealing with Gaussian processes. So if you have Gaussian processes, then you can put a specific type of distribution on empirical covariance matrices, which is called the V-sharp distribution. And if you look up for this type of distribution, you can see many theoretical results, which are quite helpful in practice. However, again, in practice, we don't always work with Gaussian processes. This assumption is sometimes violated. And if you look at some returns, for instance, for specific stocks, you can see that we have fat tail distribution. And this is something that is not well captured with random matrix theory. So here in that talk, what we are going to do is to take a step back from the random matrix theory approach and ask ourselves if we can use the geometric structure of the SPD manifold to actually build some robust statistical algorithm for the analysis of covariance matrices. So to do that, so even if we are targeting genericity, we are going to start simple, and we are going to start with some specific type of covariance matrices, which are called Toeplitz Hermitian positive definite. So why we are doing that? So for several reasons. One, because it is simpler than the generic case, and the other thing is that because we have already done some preliminary work for this type of matrices, and we presented some of this work at the JSC 21 conferences, and I'm going to come back to that afterwards. So in the following, I will denote Sn plus the set of these THPD matrices. This is a submanifold of the SPD manifold. And what is interesting is that you have a theorema from Trench and Van Blutsky, which is basically telling you that you have an isomorphism between the set of these matrices and a product space between R plus star and n-1 copy of the Poincaré disk. So this is, well known. Another something that we can note here is that we have an isomorphism as well between the Poincaré disk and the Poincaré half plane H2. So it is well known, and just by using that, we can reformulate the Trench-Van Blutsky theorem by stating that our set of covariance matrices is actually going to be isomorphic to R plus star product with n-1 copy of the Poincaré half plane. So, nothing very new here, but it's just a matter of restating the theorema in a way that is going to be useful in the following. So then, now that we have this representation of these covariance matrices, we are going to discuss the type of geometric algorithm that we can use to process this type of signals. So when we think about geometric deep learning, what we want to do is basically to be compliant somehow with some kind of transformation. So first, I'm going to define the type of transformation that we have on the Poincaré half plane. So these are given by the action of a group, which is SL2R, which has a transitive action on H2. So I denote that by the circle that you have here. And this group is going to act, so as I said, transitively by Mobius transform. So this action is going to lead to a specific structure for the half plane. You can write it as a quotient space between SL2R and SO2. So SO2 being the group of two-dimensional rotation, and we call that an homogeneous space. So we have seen that we have some kind of natural transformation acting on element of the Poincaré half plane. And now what we want to do is to build some machine learning algorithm which are going to be compliant with this type of transform. So this notion of compliant or consistency, we formulate that by the definition of equivariant. So we had, in the session this morning, several examples of, the usefulness of using equivariant approaches. So basically, very roughly, equivariants mean that you can have your operator and the group option which are going to commute. So it's basically the same of when you take the operator phi here of a transform input, then it is going to be the same as transforming the output modulo some kind of representation theory. So if you look at the literature, there is a very active field of research which is called geometric deep learning, and which aims as doing many things, and one of them is encoding the symmetry of your problem and of the data into the design of the machine learning algorithm, while also trying to work in the native geometry of the data. So you want to encode the symmetry and also to represent the data in the way that is really meaningful. So here, for our covariance matrices, we don't want to represent them as array of numbers. We want to keep the structure that we have for them. So here you have an example of the blueprint. That is something which is extracted from a book from Bronstein that is very useful if you want to have some introduction to geometric deep learning. I put that in references. So in terms of application of geometric deep learning for the processing of THPT matrices, so the specific covariance matrices that we are interested in. So at GSI 21, we presented an approach which was a SU11 equivariant neural network to process this type of matrices, and we showed that basically this was more robust and more accurate than the conventional approaches. So we were working with the initial version of the Trench-Verbinski theorem because we were representing the data into the product space of n-1 copy of the Poincaré disk, because the SU11 group, acts also transitively on the Poincaré disk. So, it was a different point of view, but the choice of SU11 was because of that. To do the equivariance and to embed that into the network, we were using generalized convolution operator. So this is what you have defined here. So it's very conventional if you look at the existing literature. However, if you try to evaluate that in practice, it's very costly because here the group SU11 is not compact and also does not have finite representation. So if you try to compute this integral very efficiently, you are going to have some issue. So we investigated several approaches to remediate that. One of them was the use of Elgason Fourier transform in the spirit of performing, Fourier analysis on groups. So, it led to some result, but it has some limitation as well. And the other thing was to try to do important sampling on the group when performing this computation doing Monte Carlo, and again, we encountered some issue. So the summary of that is that if you try to compute that for now with existing method, you can't scale the approach to industrial application. So what we now wanted to investigate is that instead of taking the point of view of SU11 acting on D, let's take the point of view of SL2R acting on the Poincaré half plane H2. So this is what I am going to discuss in the following, and I will start by defining the notion of modular forms because they will be quite useful in the following. So what is a modular form? So a modular form of weight k, this is going to be a meromorphic function which goes from the Poincaré half plane to the complex plane, and which is going to satisfy two properties. So the first one is called the modularity condition. So you can see that this is not an invariance condition, this is not an equivariance condition, this is something else. Apparently for physicists it has some well-reasoned and it's very useful, to be honest. For me it's just defined like this. And the second condition is just some kind of smoothness condition to say that you want the function to be bounded as you go to the infinity by following the y-axis in H2. So a particular example of modular form that that we are going to leverage on in the following are what we call Eisenstein series. So they are defined for weights which are even, greater than or equal than 4, and you have the formula here, gk of z is equal to sum for integer mn, such that the denominator is not equal to 0, and then you sum this fraction. So if we look at these functions, so just to give you some insight about how do they look like and the type of information that they may convey. So on the left-hand side, you have G4 plotted in H2. On the right-hand side, you have G8, again plotted in H2. You have the isomorph. So you can see that, these are very symmetrical objects. You can also see periodicity, so that's a specific type of, the modularity condition. The modularity condition being true for all the elements of SL2R. It is in particular true for, the matrix with only 1 and 0 elsewhere, meaning that you have one periodicity. And here you have the same element, but plotted in, the Poincaré disk, just to show that, we can really switch from one representation to the other. Okay. So now that we know what modular forms are, we can consider the space of modular form. So this space, we denote it MK. This is a complex vector space of finite dimension, and we know a basis for that. So here, the basis for MK is going to be constituted of the product of G4 to the power A times G6 to the power B, for A and B positive integers, such that for A plus 6P is equal to K. So that's a very powerful result, actually. Not very trivial at all. And you can find some very interesting information about modular form theory and some results in a book which is written by Stein and which I also put in the references. So now that we have that, that's a very simple corollary, but you can basically represent any modular form of weight k by a vector, a complex vector that we are going to denote alpha, which is going to represent, the decomposition of the modular form into the considered basis. So now, if we take a step back and if we think about our initial problem, so we were interested in building, some equivariant algorithm. And to do that, we will need to define what equivariant mean in our context. So here we are going to say that the function h is going to be equivariant if we can, swap the operator h and the group action. And here we just have to define a new group action that we denote star, which is the natural extension of our action of SL2Z on H2. And we extend that to the full complex space. We can apply the Mobius transform to any complex number, and this is what we are doing here. So given that definition, we can actually build what is called some rational equivariant form. So you have a paper about that, which, basically show that given a modular form f of weight k, you can build a new form, h of f, which is given by the formula that you have here, which is going to be equivariant with respect to the action of the group SL2Z, considering that definition. So basically, you can parameterize a set of equivariant form by simple modular form, which are not invariant or equivariant. So in our case, we were interested in building machine learning algorithms. So we need to train things, we need parameters. And to do that, we are just going to leverage on the fact that we know that a given modular form can be decomposed into the Eisenstein basis. So you have a vector of complex numbers to represent that modular form. And then you also know from the previous result that a given modular form can be used to parameterize an equivariant form. So you can basically, by combining the two, say that you can parameterize the equivariant form that you have here, which is defined by this equation, by just a vector of complex numbers. And this set epsilon k, ek that we are going to consider in the following, this is the one that will be the space of the target functional space that we are using to build our SL2Z machine learning algorithm. So if I go through now the algorithm into a little bit more detail, so the approach is the following. So we are considering that we have input samples which are in the product space of H2 space. We have seen from the introduction that modulo some kind of isomorphism between D, SU11, H2, and SL2R. It is possible to build equivariant architectures which are going to be equivariant to SL2R. However, this is not scalable. So here on our side, what we are going to propose is two things. The first one, to have this approach scalable, is to approximate the action of SL2R by that of SL2Z. So this is not exactly what we wanted, but at least this is something. And the second thing that we are going to do is to say that, okay, in the previous approach, we had a succession of different equivariant layers, nonlinearities, pooling, and so on, which gives you a big equivariant architectures. Here, we are going to say that we want to approximate all of that by our equivariant forms. So this is going to be our approach. So into more details, what we do, we have our input vector. Using the element in EK, we compute several features just by evaluating the equivariant maps for the several features. And then at the bottom of that, we put some specific layers which are meaningful for the task that we want to do, like classification or a generative task or whatever you want to do. So the trainable parameters of the approach are the weights of the equivariant form, the alphas vector that we have introduced, and also the weights of the downstream layers of the network. In terms of scalability, because this was the main things, so in order to compute our equivariant map, we just need to evaluate the Eigenstein series. So to do that, we can use what is called the Q expansion. So if you define Q of Z, which is the exponential here, you can basically expand the Eigenstein series into a polynomial. So you can do truncation and then pre-compute the coefficient of this polynomial and basically have closed form formula to evaluate both the Eigenstein series and the derivative that you are using to compute your equivariant map. So there is no issue to scale that from that standpoint. Now in terms of expressivity, it's a bit more tricky. So the main assumption that we are making here is that the set of rational equivariant forms that we are building, epsilon k, is going to be rich enough to approximate all the target functions that we are considering. So in the following, we do provide some evidence that at least for some of the cases of interest, it seems to work. However, we have no approximation theorem at that point. We are working on it, but this is something that we will do in some further work. So to finish, let me quickly go through some numerical results for the problem of THPD matrix classification. So the setup is the following. So we have several asset returns which are correlated here with some given covariance matrices for several financial regimes here. What we are interested in doing is to show that this type of approach is going to be more robust to the measurement noise, because in practice, when we compute covariance matrices, we do that empirically. So we have a finite number of samples. So we have some residual noise. We cannot compute the gamma exactly. So if we want to process these covariance matrices at the end, we want to have an algorithm which is going to be robust to this measurement noise. So then we build a training set where we use a variance of 1 for the noise, and we are going to build several testing sets where the variance noise is going to be set to several values, so we did that sigma epsilon. In terms of the benchmarking, so we instantiated our approach and we compared it with a fully connected neural network. So I'm running a bit out of time, so I won't detail all the setup, but the main takeaway here is that both approaches share the same number of parameters so that we can draw meaningful comparison. And the numerical result to finish, so it's really a POC, right? Just to show that it works and that we don't have scalability issue. So on the x-axis, what you have is the level of the variance for the noise that we are considering, and on the y-axis, you have the accuracy of the networks. So as you can see, so both networks are trained on the same data set with a variance of 1. And as you can see is that in orange, the accuracy of our approach is going to be higher than the one obtained with the fully connected neural network as we increase the level of variance. So we are more robust. So if we actually go back to the result we presented at GSI 21 with the approach using SU11 and D, I mean, this is very similar to what we obtained, except that here we have obtained it with an approach which is scalable. So this was the main purpose of this type of research. So in summary, we have shown that modular forms can be used to build SL2Z equivariant machine learning algorithm, that these algorithms are computationally efficient, and they could be used to scale some previous work leveraging on SU11 convolution. And we did provide some preliminary evidence supporting the benefit of the approach when working with these THPD matrices. As some further work, we do need to provide some theoretical analysis for the expressivity of our approach by leveraging in particular on approximation theorem. We would like to apply this algorithm in other contexts than THPD matrix classification. And another thing which is quite interesting from the theoretical standpoint is also to generalize to other equivariance group than SL2Z by leveraging on automorphic form, which are a generalization of modular form. So thank you very much for your attention, and happy to take any questions.
Thank you. Are there any questions for Pierre-Yves? Yeah.
Yeah, thank you. So I've got a question. So you fix the weight of your modular form that you use in the representation in advance, right?
Yes, it is fixed.
And how do you know how to fix K?
We consider it as an hyperparameter. We tried several things, so it's a bit tricky because let me go back to. Back to this here. So the vectorial space here, I mean, you know the dimension here. So if you take the weight of your modular form too small, you end up having too few elements in that space. So for now, I mean, we played a little bit, we tested several things, but what we expect is that once we had once we are going to have the theoretical analysis with approximation theorem and so on, we will probably have some insight about the number of elements that should be in this set for the approximation theorem to hold well.
Okay, so you imagine some approximation theorem along the lines. If you choose K large enough, then
yes.
Okay,
yes,
and
exactly.
you might even have something like larger than this and this, and then okay.
So what we imagine is that let's say we want to reach a precision of epsilon, for the approximation, then we should choose K greater than something.
Okay, thank you.
That's the idea.
Thank you. Any other questions? No? Okay. Let's thank the speaker again.